Welcome to Daily Papers, the podcast where we break down fascinating new research into plain English. Today, we're looking at a paper that could fundamentally change how we use AI on our personal computers.
Imagine you're chatting with an AI. You ask it a complex question. Instead of just giving you an immediate answer, what if it could spawn 100 tiny versions of itself in the background? One to fact-check, one to play devil's advocate, another to explore creative angles, all at the same time.
That sounds like a super intelligent committee meeting happening inside my computer. But wouldn't running 100 AIs at once melt my graphics card?
Normally, yes, absolutely. And that's the core problem this paper solves. It's called Warp-Cortex, an asynchronous, memory-efficient architecture for million-agent cognitive scaling on consumer hardware. It's a mouthful, but the core idea is revolutionary.
Okay, so let's start with that problem. Why exactly is running lots of AIs so difficult?
It all comes down to memory, specifically the VRAM on your graphics card. Each AI agent needs two very large things: the model's brain, which are called the weights, and its memory, which is the context of the conversation.
So if you want two agents, you need two brains and two sets of memory. For 100 agents, you need 100 of each.
Exactly. The paper notes that running just 10 medium-sized models would require about 140 gigabytes of VRAM. For context, a really high-end aiming graphics card might have 24 gigabytes. So running a council of agents has been a complete non-starter for anyone without a data center.
Right, it's just not feasible. So how does Warp-Cortex get around this massive memory problem?
It does it with two incredibly clever ideas. The first is called singleton weight sharing.
Singleton weight sharing. What does that mean?
Instead of giving each of the 100 agents its own copy of the AI brain, they all share one single copy. Think of it like a library. You don't need to give every citizen their own personal copy of every book. You just have one central library that everyone can access.
Okay, that makes sense. That solves the brain part of the memory problem. But what about the other part? Each agent still needs to remember the conversation, and 100 separate memories would still be huge.
This is where the second and arguably the most brilliant idea comes in: the topological synapse.
Topological synapse. That sounds very complex.
It sounds it, but the concept is actually quite intuitive. Instead of giving each agent the full word-for-word transcript of the conversation, they all share a highly compressed summary of the most important points.
Like the Cliff's Notes version of the conversation.
Precisely. The system uses a technique from a field called topological data analysis to identify the key landmarks in the conversation. It treats the entire context as a sort of shape in meaning space and picks out the most important points that define that shape.
So it's not just picking random words, it's preserving the core semantic structure of the conversation, but with a tiny fraction of the data.
Exactly. The paper says it can achieve a 98% reduction in the memory needed for context. So instead of needing a gigabyte of memory for a long conversation for each agent, they might only need 10 megabytes. It's a game changer.
So we have all these agents sharing one brain and one highly compressed memory. How does it work in practice? How do these agents talk to each other?
The paper describes it as a river and stream model. The river is the main AI agent you're directly interacting with. It's generating text and talking to you.
And the streams?
The streams are for the side agents. When the main river agent says something that needs, say, a fact check, it can instantly spawn a side agent into a stream. That agent does its thinking in the background using the shared brain and the compressed memory synapse.
And it does this while the main agent just keeps talking, so there's no pause or interruption?
Correct. It's asynchronous. It's like how your brain works. While you're talking, other parts of your brain are planning your next sentence or recalling a memory. You don't have to stop talking to think.
So the side agent finishes its fact check. How does it get that information back to the main agent without awkwardly interrupting the flow of conversation?
This is another cool part. It's called referential injection. The side agent doesn't just paste its findings into the text. Instead, it directly updates the main agent's short-term memory, what's called the KV cache.
What does that do?
It means the main agent suddenly remembers the information as if it had just read it or thought of it itself. The information is now part of its context, influencing what it says next without ever breaking the sentence it was generating. It's like a seamless whisper of an idea directly into its consciousness.
That is incredible. It sounds like a truly parallel thinking machine, but does it actually work? What did the researchers find?
The results are pretty staggering. On a single NVIDIA RTX 4090, a powerful but still consumer-level graphics card, they ran 100 concurrent agents, and the total extra memory required was just over 1 gigabyte.
1 gigabyte for 99 extra agents? That's unbelievably efficient.
It is. They calculate that you could theoretically scale it up to over 1,000 agents on that same card before the computation speed, not the memory, becomes the limiting factor.
So, what are the implications of this? What does it mean for the future of AI?
It means that very complex, multi-layered reasoning, what researchers call System 2 thinking, could become standard on our local devices. Instead of an AI that just gives a quick reactive answer, you could have one that internally debates, critiques, and refines its thoughts before it ever gives you a response.
And because it's on your own machine, it's private, it's fast, with no internet lag, and there are no per-use costs you'd get with a cloud service.
Exactly. Warp-Cortex provides a blueprint for turning a single AI model into a collaborative council of thinkers. It's a fundamental shift from thinking of AI as a single monolithic process to thinking of it as a shared resource for massive parallel cognition, all on the hardware we might already own.